All right, so let me start by welcoming all of you to IIT Kanpur. And so we have about half an hour or 45 minutes in which we can discuss how this particular course, Introduction to Electronics, is offered at IIT Kanpur. It's I think the courses of similar nature which are offered at other institutes are a bit different from what we do over here. So what I'll very quickly do is, there isn't enough time, but quickly tell you what the course objectives are. These are obvious: analyze and design electronic circuits. That's the first obvious objective. Build, along with this particular course, we have a lab attached. So build and test circuits in the laboratory. And the last one, recognize interrelationship of electrical engineering with other fields of engineering and appreciate the multidisciplinary nature of the engineering fields in general. Now, this is a course that we offer to all the students. Whether a student is of civil engineering or mechanical engineering or chemistry or physics or whatever, all students take this particular course. And this is offered in both the semesters. Topics are, I'm not going to go over the details of all of this. You can see that there are 3 particular modules in this particular course. The first one, roughly each module is about 13 lectures. So total of about 39 or 40 lectures. So the first module is basically analysis of linear circuits, different techniques that are used for analysis here. The second module introduces students to semiconductor devices and analog circuits. And the third one is the digital. Now, in many places, what is there is there's usually a full course on analysis of circuits. In many of the universities, full course on analysis of circuits. There's a full course on the second module, devices and analog circuits, and there's a full course on digital circuits. Now, here, as I said, this is an introductory course given to all the students. So what we try to convey is a very broad picture of what electronics is. So it's not just for electrical engineering students. Those students would, of course, later on in the curriculum, they would take a full course on devices, electrical engineering students, and a full course on circuits, analog circuits, and digital circuits, and all of that, right? But for the rest of the students, this is the main course. And so the idea is to introduce them to the field of electronics. And, these things we'll share, so there are books and all that we use, so that is there here. And our usual evaluation is, as you might have learned, we usually have a midterm exam, we have a final exam, so the way the course runs is, every week there are 3 hours of lectures, and 1 hour of tutorial, and 3 hours of laboratory, right? So total contact hours are 7, 3 lectures, 3 lab, and 1 tutorial. And we have a distributed evaluation scheme: midterms, tutorials, quizzes, labs, and all that. Anyway, so that's the point is, one of the, let me come back to, not go into the details. One of the difficulties in teaching this particular course is many students, students from other discipline. We have no problem with students from electrical engineering. A student from other discipline, let's say a mechanical engineering student or a chemical engineering student, has this question: why should I study electronics? All these things that you are teaching, how is it relevant for me? And that's very important, because unless the student is motivated, he or she is not going to learn, right? So with that in mind, what I'm going to do is, aside from all the details that are there, circuit analysis, diodes, transistors, and all of that, there is a big picture about electronics that we feel as all students must get from the particular course. That big picture is what I'm going to talk about. See, we have no problem with convincing students. In the first year, we have students taking mostly science and maths courses, right? We have no problem in convincing them why science is important for you, right? Engineering rests on science, and they're very easy to give problems. A lot of interesting examples that we can give. You take an air conditioner, and you know that you require various principles of physics that you see here. The gases liquefy under pressure. When a liquid vaporizes, it takes heat from the surrounding. You see a force acts on a conductor carrying current. All these different principles of physics and chemistry and all that, you see their applicability, right? So students have no problem in understanding, yes, I've come to do engineering, but I know that engineering rests on science. So I must have a good grasp of the different principles of physics and chemistry and all that. There's no difficulty. The reason why I'm saying is, they have a difficulty with saying, why do I need to do electronics? Okay, a civil or a chemical engineer. Similarly, a student doesn't have a problem in saying, why am I doing so many maths courses? Because every problem, engineering problem that all of you know, every problem that I take is eventually reduced to a maths problem, right? If I take a diode, I describe it in terms of a mathematical equation. If I take a circuit, I reduce it to a mathematical equation, a nonlinear equation that I need to solve in order to understand how a circuit works. So they have no difficulty. Why am I studying maths? Well, all the problems that are there, we eventually model them and it becomes a mathematical problem, and then we need to solve in order to understand the problem that one is trying to do. So they have no difficulty with appreciating, why am I doing maths, why am I doing physics and chemistry and other things. Why electronics? Is electronics as important as maths? You're asking all the students, chemistry students, physics students, mechanical engineers, you're asking all of them to do electronics. Is electronics as important as physics? Is it as important as maths? Why are you asking all of them to learn electronics? So I think that's the big picture, that's the big question that needs to be addressed in a course like this while you go through the details, right? And so this is what I'm trying to highlight. Why do we require all students to take electronics? And this is, for example, the way I'm giving my perspective on this is how, for example, when I interact with students, the kind of perspective that I try to give them is, it's not hard for anybody to appreciate this, that modern life is defined by electronics, has been heavily impacted by electronics, and all of us can give a huge range of applications, and you pick anything in your surrounding, you find there is electronics embedded in it. So the importance of electronics can be very easily highlighted in terms of all the the gadgets and other things that we see around. But beyond this, the way that I try to convey this particular one is the following. In terms of 2-3 simple statements. One is, no matter what we do, every action requires energy. Anything that you try to do is an obvious self-evident statement. Every action requires energy. Fine. The other one is, electricity is a very useful form of energy. Not directly. Our direct interaction with electricity is often painful. We get a shock. So it's not directly electricity is useful for us. For thousands of years, mankind survived without any use of electricity, right? So electricity is a very useful form of energy because of the following. Because it can be precisely controlled and easily converted to other forms of energy. These are two very, very important things. No other form of energy, if you take, can be as well controlled as electricity. And it's readily converted. We all know that electrical energy can be converted into heat, light, motion, anything that you name. And from these two, it follows why electrical systems are so important. See, the first statement says, no matter what you are thinking of doing, you require energy, right? And the second statement is saying that electricity is a very useful form of energy. Why? Because I can precisely control it. I can precisely control it. Control it means what? I can make it do what I want. Once I control something, I can make it do what I want. So it can be precisely controlled and converted to other forms of energy. And therefore, electronics offers capabilities that can be exploited by almost all engineering branches. This is the diagram that we use. No matter which engineering branch you're thinking of, right? You're playing with energy. Energy in some form, you're trying to do something. For example, a diagram like this, for example, you're trying to do something in your environment. Whatever you're interacting with the environment. What you can do is, well, you can take whatever your interaction, whatever your input is to the environment, you can convert it using sensors into an electrical form, do lots of interesting processing in the electrical form, and then convert it back into whatever is the output that you really want. A very simple example, let's say I'm talking in this particular room. I want my speech to be audible to all of you. So my interest is in the audio signal, right? My audio signal has to travel in this classroom environment. Now, directly I may not be able to reach, then we know that audio signal. We have a very simple example that we can use to the students. Microphone converts it into an electrical signal. You can do lots of very simple processing, is simple amplification, right? But besides amplification, you can do lots of noise reduction and other things as well. So you take this electrical signal, do your processing, bring it here, convert it back into a audio signal and back into your environment. You don't need electricity directly, but the processing in the electrical domain enhances whatever you're trying to do, right? So the point is, addition of an electrical subsystem can enhance almost any engineering systems here. It could be a mechanical or a chemical system. Whatever you're trying to do, you can take your inputs and you can convert it into an electrical input with a variety of sensors that are available. Do your processing in the electrical domain. Why? Because it's so easy. It's so convenient to do things in the electrical domain as compared to in any other domain. So you do your processing in the electrical domain, use a actuator, convert it back into your system, feed it back into your system. So the point is, every system, mechanical, chemical, whatever you're talking about, every system can benefit from use of electrical subsystems here. And that's why you pick up any engineering system, you'll find electronics embedded in it. Otherwise, for example, and there are numerous examples. For example, you take in a car an anti-lock braking system, right? Braking is a mechanical thing. You're applying pressure onto a wheel to stop rotation, right? But when you come to an anti-lock braking system, so on each one of those wheels, there are sensors mounted, and you get an electrical signal, and you find out which wheel is moving faster or slower, and thereby you adjust the pressures, and thereby you have a intelligent braking system, an anti-lock braking system with the help of an electrical this thing here. So the point that, and as I said, there are, each one of us can find many applications. There are smart buildings, and there is a hearing aid and all kinds of things that are there here. So the point is that every system can benefit from use of an electrical subsystem here. So whatever you're trying to do, convert your inputs, convert your signals into an electrical domain, do your processing in electrical domain, convert it back. So that's the big picture. Big picture that everybody should carry as to how electrical engineering can help in their domains. The thing is, yes, you can do nice things with the electrical signal. That becomes even more powerful with the progress of digital processing here. So you can see from this particular diagram, as you take these sensors and you convert it into an electrical signal. Well, the normal signals that you get normally from the environment are analog in nature. They are continuous in time, continuous in amplitude, they're analog signals. You can do some processing. You can manipulate analog signals. You can amplify them. If you want, you can multiply two analog signals. If you want to take a square root of an analog signal, it becomes very hard. You can take a log. If you want to solve a differential equation, it becomes very hard in the analog domain, right? So very soon, what we can do is we can take the analog signal, convert it into a digital signal, and you enter into the domain of digital signal processing. And then, of course, we can take a digital signal back to analog, convert it back D to A converter, do some more processing, and then convert it back into whatever signal that I want here. The real power of electronics has come about because of this part here, digital signal processing. Digital circuits that we introduce to our students are, simple circuits, gates and counters and things like that, simple circuits. But what we have to convey to them is the power of digital circuits. And especially the digital circuits have, they are actually the programmable digital circuits. So digital circuits are not, they are programmable hardware. So what it takes us again into a domain of, basically, it's not just the things that you're doing in hardware, but you can also write an algorithm or a software, right, which runs on your hardware and does all kinds of interesting things here. So this potential of now, whatever you're trying to do, converting it into an electrical form, and then digitizing it, getting it into the digital domain, and then you can either do things in digital domain. Again, it's a little bit hard doing everything in hardware, or you run your whatever algorithm, whatever you're trying to do on a programmable hardware, microprocessors, microcontrollers, and things like that. So that's where the real power of electronics comes in. So when we are teaching digital circuits, we have to convey this. Why are the digital circuits? So through these simple examples, we have to convey how digital circuits have really revolutionized all systems, mechanical, chemical, or whatever systems that you take. The other interesting thing that has been happening recently is it's not only that you can do you have a hardware, programmable hardware, so you write a software which runs and does your processing. Communication has become so cheap that things don't have to happen in your system. You communicate, you send it out to a server somewhere in the cloud, so it gets processed there, and then it comes back to your system, and then of course you convert it back and you interact with the environment here. So the point that I'm trying to convey is that this is the big picture of electronics, how it comes in and affects everything, right? So while we are doing our linear circuit analysis, while we are doing our amplifiers, while we are doing our digital circuits, sometimes this big picture the students don't get that big picture. They miss that. So the attempt should be that how do I illustrate? Whatever I'm doing, a first year or a second year course doesn't allow us to do a lot of complicated things. We can only handle simple things. But the idea should be how do I take these simple things and at the same time, how do I illustrate? How do I illustrate this big picture here, right? So when I'm doing digital circuits, I need to show to the students that, look, where does the power of digital circuits come from? The power of digital circuit comes, besides doing things in binary and all that, comes from the fact that we have a programmable hardware. And programmable hardware means doing things in software, right? So doing things in software becomes far more easy writing a code than making a circuit specifically which does that particular thing, whatever task you are talking about. And as I said, we can find numerous examples of how this is done. So our courses, as you can see, is also structured like that. We do introduce students to analog signal processing, amplifiers and other blocks, but a lot of our course is devoted to the digital part here. The digital part is extremely important, and also how the signals get converted from analog to digital and digital to analog, where losses occur. Whenever you convert, there's a problem of accuracy. There's 12-bit and 24 bits and all that. So those are important aspects that are there. Coming back, so that's the big picture of how electronics comes in and affects everything that one does. And in that sense, just like every problem reduces to a mathematical problem. As I said, every engineering problem reduces to that. So similarly, every problem that you're trying to handle can benefit from converting it into an electrical problem, converting it into an electrical signal. And in that sense, the electronics course is as important. I'm not saying it's more important, but as important as a course in physics or a course in maths that you see here. Every system, chemical, mechanical, whatever you can think of, all scientific instruments that you pick up, they all have embedded electronics in them. So everything can benefit from electronics. So that's a big picture that needs to go. Aside from that, there are, in each one of those topics that you see here, I have a whole list of topics. The other thing that we find is, there are some students who, when you teach a RC circuit, a resistance and a capacitance, and you look at transient analysis and sinusoidal and all that, there's some students that are okay, who love things which are abstract in nature. They're happy with the waveforms and things. There are other students who want a connection to reality. Okay, I'm doing an RC circuit, but what good is an RC circuit? A resistor and a capacitor connected together. What good is it? Why am I learning it? This constant questioning in some students' mind comes in as to why am I doing it? How is it relevant? As I said, there are other students who are perfectly happy. Maybe they have a mathematical bent of mind. They're happy with equations and they love it. But the other students who always are craving for a contact with real life. And so that's the other important, and there are beautiful examples sitting there. For example, if you take an RC circuit, right? If you take an RC circuit, there are very nice examples that are sitting there is that, for example, when you take a DRAM, a dynamic RAM memory, and a dynamic RAM, if you look at it, is a transistor and a capacitor. Each cell is basically a transistor and a capacitor. So when a student is studying capacitor, of course we say Q equal to CV and all those equations that are there, but a capacitor acts as a memory. It's a basic memory element that is used everywhere. Capacitance is the memory element. And then when you make a DRAM cell, this transistor, it acts as a resistor here. So it's basically an RC circuit. And how often do you have to recharge your DRAM? How often do you have to refresh your DRAM? How do you get that, the time at which you need to refresh your DRAM? That comes from a simple RC circuit analysis. So, showing to the students that, look, the DRAM that you put in your cell phones and your laptops and all that, DRAM, at the heart of DRAM is nothing but a capacitance, which acts as a memory element. And the RC circuit that you are studying, it helps us understand, for example, the refresh rate of a DRAM. So examples like this, once they are brought, it of course makes things more interesting. And another example is from real life is your LCD panel. This panel, the LCD liquid crystal display, if you go behind it and look at liquid crystal display is also somewhat like a DRAM. In each liquid crystal display, there's a transistor, there's a liquid crystal cell, and many of the properties, if you want to understand of a LCD display, again, you need to understand an RC circuit. An RC circuit is relevant to understand how a liquid crystal display, for example, works. We can come up with examples like this which connect simple concepts that you see here in each one of them to something which is there in real life. There are many such examples that if we make an effort, it can be found. And so those act as, bring connection to everyday life and serve to motivate and, helps the student learn. The other thing is, I'm just trying to take a few examples to illustrate. The other thing is, many times, as I said, there are electrical engineering and like in other disciplines also, there are beautiful concepts that are sitting there, which are valuable not just to electrical engineers, which are valuable to every stream. Take this example. For example, when we do a sinusoidal analysis. When we do sinusoidal analysis, we all use, as electrical engineers, we use phasors. We use phasors to help us calculate the voltages and currents and all that that are there here. But if you look at it, what we are doing, that directly adding, subtracting, and multiplying sinusoidal variables is a bit difficult. What we are doing is we are converting it into complex variable, and we are performing algebra in the complex domain. And then, after we are done, we transform it back to the sinusoid. So this general picture of when you are trying to analyze, the analysis in one domain, we all know analysis in one domain may be a little difficult. What you do is you convert it into another domain. And you convert it into another domain, Laplace transform, Fourier transform, all of that, you convert it into another domain and it becomes easier. You do processing in that domain and then you convert it back. So this is a very general principle, very, very general principle which is important or which has applicability in all spheres. We just talked about, if things are difficult to do mechanically, you transform it into an electrical signal. Do everything in the electrical domain, convert it back into a mechanical signal. It's the same principle that you see here, applied to analysis. In analysis, computation in one domain is difficult, convert it into another domain, do everything, convert it back. Right. So as I said, so many times when we are discussing these phasors and all of that, we get bogged down into the details. Phasors, addition of phasors, and calculating impedances and all that. Those are all fine. But what happens is a year or 2 years down the line, a mechanical engineering or a chemical engineering student is not going to remember anything about phasors. He or she will forget almost everything. But that big picture, that deeper principle that is there, maybe they'll remember if it is emphasized. The deeper principle is far more important than any addition of any calculation of an impedance and all that. The deeper principle may have applicability in many other domains. And similarly, for example, when we look at an amplifier. So when we look at an amplifier, this is a common emitter amplifier. And when we teach students how to design this common emitter amplifier, the design is complex. You have to bias the transistor, make sure that the circuit biasing point is stable, and then you have to look at input resistances and output resistances and gain and bandwidth and things like that. Even for a very simple circuit, the design is relatively complex. Now, there's a very powerful principle sitting here. So design of an amplifier is difficult. Only people with very, very specialized knowledge will design amplifiers. But what solutions did electrical engineers come up with? They invented the op-amp. They invented the operational amplifier. An operational amplifier is, again, this is a very general engineering theme of whether you do a custom or you do a semi-custom design or you do a standard design. Custom design meaning, as all of you know, given a specifications, you do design according to that specifications only, right? Op-amp is a beautiful example of a semi-custom design in the sense that a lot of people want amplifiers. You know, they have a signal and they want to amplify it. A lot of people want amplifiers. But designing amplifiers is very complex. Only very few people with specialized skills can design amplifiers. So what do? A lot of people want it. Now, you can't take, a person who wants an amplifier, he or she may want only an amplifier in quantities of 10 or 20. That's it. So you can't have a dedicated engineer design an amplifier for that, for 10 or 20 volume. That's not feasible. So the solution is a semi-custom design, an amplifier, an op-amp. So an op-amp is a very complex circuit. Very, very few people can design an op-amp, very complex circuit. But at the same time, it's a complex circuit which is a user can take it and customize it. Right? The customizability is a very important feature, a very, very complex thing, but with very simple interface. And anybody, you don't have to be an electrical engineer, a civil engineer or whatever can take and make his or her own amplifier. The op-amp is there, all you need to do is add a resistor R1 and an R2 and the ratio gives you the gain. So apart from the fact that you have an op-amp and you can do very interesting thing, what it conveys is a very important principle. A very important principle of semi-custom design. So you do a design which is very complex but very simple interfaces. Very simple interfaces and allowing a person, a non-specialist to add something to it and customize it to his or her requirements here. So op-amp in a very beautiful way illustrates that particular one. It's a very popular, all of you know that op-amp based designs are popular because of that. Microprocessors are another example. Very complex circuits, microprocessor, extremely complex circuit, but very easy to use. Anybody with a, who knows the C language can program a microprocessor and then use it to his or her advantage here. So this idea of a complex design, very complex designs, but with simple interfaces and which can be customized. So that's a larger theme that one can illustrate to our students when we are talking about, let's say, an op-amp based circuits. So my point is, it's not just a inverting amplifier or a integrator or a differentiator or whatever. Those things are there. The details are there. But in each one of them, there's a larger theme. There's a larger theme, there's a larger principle which are valid in many domains. It's not just in electrical domain, they are valid at many, many places here. The design philosophy that we use here is valid in other places as well. So, in fact, whatever, so the other point is, we all know that, whatever we teach, it touches only a fraction of what really exists. The world of, in any particular field that you take, the amount of material, the amount of knowledge that is there is huge. And in the limited time that we have, we cover only a very, very small fraction. We cover a very small fraction of what is really there, right? So then it becomes very important is that whatever we cover, it of course covers that particular part, but it also illustrates a larger theme. Those larger themes, those big pictures, they are not too many. The important principles of design, the important principles of analysis, there are few important principles of design. So while we are doing these little things that we are doing here, an op-amp based designs or whatever, at the same time, if we can make sure that it illustrates that larger theme. And this is, I just put this is a part of a poem that, that acts as an inspiration for me. This is a poem by William Blake, and the first line here, to see a world in a grain of sand. right? So in a grain of sand with the right perspective, you can see the entire world. Of course, that's a poet's imagination, right? You can, in a grain of sand, you can see or you can see a heaven in a wildflower. So our point is that whatever little things that we are teaching, small things, RC circuit or a op-amp or whatever that things that we are teaching, it can illustrate some very large, very powerful principles. If we can do that, then I think whatever we teach will be more lasting. Because many times the details these students would forget. The details they would forget, but some larger principles, if you keep on emphasizing it and keep on illustrating it, those principles, very important principles, they will carry maybe throughout their life. Right? So let me stop here, and as I said, time is limited. Any further questions that you have? I don't know how much time I have left, but what we can do is we can take your questions and this thing. I have my contact address and other things that you can get as part of if you want to discuss further. But any questions? Any questions regarding the course? Nobody has anything? Yes. This is a second year course. We give it in the second year. Second year, yes.
But actually, you are talking about the data processing and many advanced applications.
Yeah.
In second year, it may be very difficult to get understandable.
You are right. My point is not to talk about very advanced things, but my point is to use simple things to illustrate. To illustrate, I'm not going to talk about, for example, let's say how a microprocessor works or how all those things. But the principles, in simple terms, one can talk about it. In simple terms, one can talk about.
In many universities, actually, first year basic electronics course is there.
Yes, we used to teach it the first year also.
So that is very different from this course. This is, I think, an advanced level.
This is, as I said, our course is a bit different from the courses that are taught in. It has elements of different subjects, digital, analog. So as I said, this is the only course that our non-EE students take. And so what we try to convey through this, that give them a flavor of analog also, digital also, circuit analysis also, so they get a bigger view, picture of what electronics is all about. So for an electrical, if I had to design a course separately for an electrical engineer, it may be different from this. But this is given to, most of the students taking it are non-EE students.
Sir, but the syllabus, to cover the syllabus, the time will not be sufficient, no, sir?
Well, the syllabus, if I, let's see the syllabus, here, right? You can see how we cover. Fundamentals of electrical circuits, 3 lectures, RLC 2, 4. As I said, you are right, the first block that you see here, a complete course can be given on the first block, and in many places a complete course is there for the first block. Similarly, for the second block also, a complete course is there. But as I said, to a mechanical engineering student, he's not going to come and take 3 courses.
But then he'll be left with half-clear concepts.
Not half-clear concepts. The thing is, does a mechanical engineering student need to know how to design a bipolar amplifier? What is the need of a non-EE student? See, suppose this is a dilemma. Suppose I take a course and I go over the fundamentals of that particular course, lay a nice foundation, right? Lay a nice foundation, which is very good for EE students, because on that foundation we are going to build. EE students will take a second course and a third course, and on that foundation you will build. But for a mechanical or a chemical or whatever student, you lay a nice foundation and then you don't build anything on top. Is the foundation any good? You just lay a nice foundation and leave the foundation after that. So the point is, for those students, it's far more important to know as to what electrical engineering can do for them. How can I use electrical engineering? That's why I was trying to emphasize how is electrical engineering important? How can they benefit from it? And for that, you don't need to go into, in rigorous details of maybe resonance or third order electrical systems and things like that. Right? That's what I'm trying to emphasize. It's not the details in each one of them, it's the big picture which is important. If we can convey that, then I think we would have succeeded in conveying the purpose of a course like that. Anyone else? Okay, I guess. All right, okay, so we'll stop there.